section 1. Using basic integration formulas. And pretty much what we have to do all right, so what's going on here is this. The fundamental theorem of calculus stated that once we find a antiderivative of a function, then we could find the definite integral, which means we could find the area under a curve or the volume of a solid. That's what we started off with. The problem is finding the antiderivative. It's got to fit into some formula, because we know so far this. If we have this, what would that integral be? Ln u plus c, because it's an indefinite integral. Right. But we're going to see in here today that it won't be that simple all the time. We're going to have to use algebra, trigonometry, and rational rules from algebra to fix these equations so that we can make them fit, make them work. Here you go. So that's going to be the hard part for this section. Is we're going to be taking these equations and do whatever we have to make them work, to make them fit. To make them fit those formulas, that the table that you have. Let me see if I have an extra one of that. Yeah. So what we're going to have to do is I'm going to give you equations, examples, and we're going to have to make them fit one of these. And then once we make them fit there, then we have the integral already done for us. So that's the easy part. So let's begin. Let's look at example 1. Oops. Let me write that one down. Evaluate squared minus 3x plus 1, 2x minus 3 dx. What this first one's going to show us, what we're going to do here in this first one, sometimes we need to rewrite the integral to match one on the chart. What does that mean? How would we rewrite this one to make it fit? So which one do you think is going to fit on our table? Which one do you think is going to fit? Actually, it may not be on this one. It's just one of the basic ones. Well, let's look at this one. What do we know? Always look at, first off, always look at the denominator and inside the operation. So let's focus on this term here. How are these two related? How are these two terms related? Exactly. This, take the derivative of this, we get this. So we know that our u is going to be x squared minus 3x plus 1. When we find du, it's going to be 2x minus 3. Two x minus 3 dx, because we're taking a derivative with respect to x. We're doing, what are we doing here? We're doing a transformation, right? A substitution, so to speak. So what our equation is going to happen is this. We're going to transform our equation to that. But what is wrong with this? What's missing? We can't just do a transformation just of the operations. We also have to take with respect to the bounds. So what do these bounds have to change to make them fit our UDU function? To find the new bounds, we take A and B and plug them into U. When I say A and B, what am I talking about? Yeah, the upper and lower limits, right? So U is a function. Okay, so when x is 3, what do we get? 3 squared minus 3 times 3 plus 1. We get 1. So our lower bound starts at 1. Our upper bound is at u at 5. Five squared minus 3 times 5 plus 1. 25 minus 15 plus 1. So for us to do our transformation, our substitution method, we changed it from x to functions of u. Now, can we take the integral of that? Yeah. To take this integral, we got u to the power negative 1/2 du. And what's the integral? What's going to be here? No, because it's radical. If it was du over u, it'd be great, but this is du over square root of u. So what's the integral of this function here? How do you take the integral? Yeah, so it's going to be negative 1/2 plus 1 on top, negative 1/2 plus 1 on the bottom, from 1 to 11. So it's going to be u to the power 1/2 over 1/2 from 1 to 11. This 1/2 on the bottom becomes 2 u to the power 1/2 from 1 to 11, which is 2 square root of u from 1 to 11. Okay, notice that since we made our transformation from x to u, all we have to do here is do the bounds. And this is our answer, wherever that's going to be, that's our answer. Put it in your calculator and you get an answer. Here's number 2. There's number 2. All right. Okay, let's look at number 2. Okay, what this one says is complete the square to evaluate. Sometimes, again, looking at the equation, we may need to complete the square. So what we're evaluating is this equation. What we have to do is complete the square on the bottom. So what we have here is 8x minus x squared. Set it equal to 0. Let's rewrite it. When completing the square, well, actually gets, no, let's go. We have to have a leading coefficient of 1. So we change the signs across the board. So we divide by -1 or multiply by -1 or just change the signs across the board. On the left hand, okay, now you have to add. Well, remember, a quadratic equation has this form in standard form. What we have to do next is add b over 2 squared to both sides. So you add b over 2 squared to both sides. On the left side, only do inside the parentheses. The right side, work it out. So on the left-hand side, we have x squared minus 8x plus 4 squared equals 4 squared, which is 16. Now to complete the square, take whatever's under the square and the first sign. Put them in there. So it's x minus 4 squared equals 16. Now move the 16 across. Because we're not solving for x. We're simply rewriting the function. Now, since up here we took out the negative sign, we have to put it back. So multiply everybody by -1. So we have negative x minus 4 squared plus 16 equals 0. So the factored form, or the complete the squared form, is like this. Why is it this way? Because that's the way our original equation was written or structured. So this whole thing goes in here. (16 minus x minus 4 squared). Okay. Now, this is important. Why do we put it this way? Look at your table. Let's look at all of them that have a square root on the bottom. This one, this one, this one, this one. So we know it can't be 19 because there's no square root. So it can't be 19. It can't be 20 because we don't have a coefficient of x. It can't be 21 because we don't have a plus. So it's either going to be 18 or 22. What's the difference between 18 and 22? A and x are switched. Since we have a number minus the variable, so we're going to use Rule 18. In order to use Rule 18, (16) is made of what? 4 squared. And this is our U. So it's A is 4, U is X minus 4. So we have A squared minus U squared. This is what we have. Makes it much easier to write than that. Since that matches our Rule 18, we know that the answer is the inverse of sine U over A plus C. The inverse of sine U is X minus 4 over 4 plus C. And there's our answer. Again, the hardest part of this is remembering all your rules from algebra. How many of y'all remember how to complete the square? How many of y'all remembered how to complete the square? Yeah, exactly. So, I mean, if you're not familiar with it, it's Greek. So, again, this is very, very, very algebra and trigonometric rule intensive. Yeah. Well, yeah, because remember, our formula has to be A squared minus U squared. So, since we have our number here first, 16 is A squared. That means A is 4. So this is 4 squared minus that squared. A squared minus U squared. That was number 2. Let's look at number 3. Evaluate the integral. Cosine x sine 2x plus sine x cosine 2x dx. Use trigonometric transformations, properties to change your equation. What I'm saying here is, do we know what cosine x sine 2x plus, look at your cheat sheet that I gave you a couple weeks ago. What is cosine x sine 2x sine x cosine 2x? So look at your, identities. That's what it's, identities. We use trigonometric identities to transform our equation. A good sign to see these is this. Whenever you have sine, cosine, sine, cosine, if it was cosine, cosine, sine, sine, then that would be a cosine connection. Since it's opposite, we know it's a sine. It's a function to do with sine. We have two angles, so it's the sum of two angles. This angle plus this angle. It's the sum of two angles. The sine rule. So what this equals is the integral of sine x plus 2x is 3x. What this rule is this. It's sine a plus b is equal to cosine a sine b plus sine a cosine b. This is the rule you're looking for. It's a sum of two angles. So now it's a lot easier to integrate sine 3x. What are we missing? In order to make this an integrable function, what are we missing? Right now it's sine u du. What is du? If u is 3x, what is du? 3. We're missing a 3 here. So that means we have to put a 3 out here. So the integral of sine is what? Negative cosine 3x. Plus c. So the answer is really negative cosine 3x over 3 plus c. That's the way you could write it. So far, so good? Again, I'm not going to lie to you. It looks simple, but it's difficult because you have to have all your cheat sheet access available. The trig ones are easy. It's the algebra ones, because the algebra ones has 16 weeks worth of information you have to know. All right, let's look at example 4. Evaluate from 0 to pi over 4, 1 minus sine x dx. What's wrong with this one? If we took the derivative of the denominator, would we have an ln function? Do we have du over u? The answer is no, because the derivative of negative sine would be negative cosine, and we don't have that on top. And we can't put it there because it's a function of x. So what we look at here is this. What we have right now is that whenever you have a continuously differentiable function on the bottom, the sine never ends. How do we get rid of it? We need something on top. So when you have rational equations, you may need to multiply both top and bottom by the conjugate. So what would be the conjugate here? We have 1 minus sine x. So we multiply top and bottom by 1 plus sine x. You said it, but you didn't say it loud enough. So on top, we simply have 1 plus sine x. And on the bottom, we'll have a difference of two squares. So 1 squared minus sine squared is what? It's cosine squared. It's a trigonometric identity. Now, since we have a monomial on the bottom, we could split them up. So we have 1 over cosine squared x dx plus sine x over cosine x dx. One over cosine squared is what? Secant squared. So we have on this one, we have sine x over cosine x times 1 over cosine x. That's what this one equals. So sine over cosine is tangent x. 1 over cosine is secant. So look at your cheat sheets. What is the integral of secant squared? Yeah, integral of secant squared is tangent. So this is going to be tangent x from 0 to pi over 4. And the integral of tangent secant is secant. So we have tangent secant. What we have here is tangent x from 0 to pi over 4 plus secant x 0 to pi over 4. Tangent pi over 4 minus tangent at 0 plus secant of pi over 4 minus secant at 0. Tangent of pi over 4 is sine over cosine pi over 4, which is square root of 2 over 2 or square root of 2. This is 1. Tangent at 0. What's tangent at 0? Sine of 0 over cosine of 0 is 0. Secant pi over 4. That's 1 over cosine pi over 4. Cosine pi over 4 is square root of 2 over 2. So it's 2 over square root of 2. One over cosine is 1. What's that? This cosine and sine at pi over 4 is 45-degree angle. Pi over 4 is 45 degrees. So at 45 degrees, sine and cosine are both the same. They're both square root of 2 over 2. So this is square root of 2 over 2. This is 1 over square root of 2 over 2, which makes it 2 over square root of 2. Okay, we can rationalize this. Square root of 2 over square root of 2. So we have 2 square root of 2 over 2. One minus one is that, so it's simply square root of 2. Again, you have on your cheat sheet, you have the trig identities and the unit circle. Have those at your ready at all times. You'll need those cheat sheets a lot. So whenever you have rational equations, especially with trig, you may need to multiply by the conjugate. What example was that? Let's list example 5 now. Evaluate 3x squared minus 7x, 3x plus 2 dx. Part. No, I don't. All right. What we're looking at here, we have a rational equation again, but not of trigonometric equations. When you have rational equations, fractions, algebraic in form, first you see if factoring will help, or is the denominator, one is a derivative of the other, and it doesn't work that way. Again, you have a whole series of things you can look at. In this case, since the exponent on top is bigger than bottom, if you have an improper fraction. Why is this an improper fraction? Because the numerator is bigger than the bottom. Use long division or synthetic if you can. And divide them. Does everybody remember long division? Okay. Long division is simply, here's your denominator, and here's your numerator. If there are any spaces missing, in other words, if this was 3x cubed minus 7x, I would have 3x cubed plus 0x squared minus 7x. You have to have each column allocated with a number, looking at the variables. Look at the first terms. What times 3x gives me 3x squared? X. So x times 3x gives me 3x squared. X times 2 gives me positive 2x. Change the signs and add. Your whole objective is to get rid of the first term. So it's negative 9x. What times 3x gives you negative 9x? minus 3. So negative 3 times 3 is negative 9x. Negative 3 times 2 is negative 6. Change the signs and add. What is this number? That's the remainder. So our answer here, what this now becomes, is x minus 3 plus 6 over 3x plus 2 dx. Because the remainder goes over the denominator. What's the integral of x? X squared over 2. Integral of 3? Now the integral of 6 over 3x plus 2. Let's look at this one. The integral of 6 over 3x plus 2. So if we took the derivative of the bottom, what will we get? 3. Is there a 3 on top? This is 2 times 3. So this 2 is simply a constant since it's not really needed. So if this was u and du is 3, we have d over u, which becomes what? Du over u becomes ln plus c. So this last part becomes 2 ln, the u is 3x plus 2 plus c. And there's your integral. Again, it's easy once we get started. But if you don't see where you're supposed to start, any questions so far? So what are the methods we used so far? We're in example 5. What was the first example? What method did we use there? Here's example 1. Oh, yeah. In example 1, we just did direct substitution. That's u, that's du, so it worked. Example 2, we needed, because since we have all our rules that have square roots, have a squared and u squared, we needed to get to complete the square. Example 3, where's example 3? That one dealt with trigonometric identities. Can we rewrite this trig formula as a simpler form? Yes, it happened to be the sum of two angles. Example 4, since we didn't have a du over u, we used the conjugate rule and multiplied by both top and bottom by the conjugate. And example 5, since nothing is in there, we simply used long division. Can you do long division in trig functions? Invent it. If you could invent it, you probably get a Nobel Prize. But not that I know of. It's just that if it's algebraic and you don't see a connection between the two, because it's usually the denominator of the top. So if you take the denominator and take the derivative of it, is it the top? No, it's bigger. It's improper. So long division. Let's look at example 6. Evaluate 1 minus x squared, 3x plus 2 dx. Okay, in this example, we have a radical on the bottom, and it's in the form a squared minus u squared. But is the top in any way, shape, matter, form du? Sometimes we can separate the rational equations into smaller equations. What does that mean? Since we have a sum or difference on top, we can separate them into two separate ones. All right. So looking at the first one, let's look at this as our u. We have to define a u and du. If our u was 1 minus x squared, then du would be minus 2x. Dx. Why did I put a dx behind it? Well, yeah, because u is a function of x. When we take the derivative of x, it's, what is that called? Implicit differentiation. I'm taking derivative of function with respect to x. I'm doing that. So what do we need in our equation? We need to have a negative 2x on top. Do we have a negative 2x on top? We have an x. So this is a constant. It can come out in front. And I could put a -2 right there. If I put a -2 there, I got to divide it out in front. So now the first one is a constant, du over square root of u. Did everybody see what I did? Since this 3 didn't do anything for my function, it's a constant. I took it outside. Since I needed a -2 in front, I could put a -2 in front, but I also have to put a divide it out in front because they cancel. And then for this one, I just take the integral of this. The integral of u to the power -1/2 this is going to be u to the power 1/2 over 1/2 -3 over 2 2u 3, so we have -3 square root of u. That's this first part. That part. Yeah, but what was u? -3 1 minus x squared. What about this one? Now for this one, since there's nothing on top of it, it's just a 2 dx over 1 minus x squared. What can I do there? Since there's nothing on top, let's look what we have here. Remember, all these trig identities all have a dx on top. So which one do you think this one will fit? Which one? Yeah, number 18. A is 1, u is x. Because it matches a squared minus x squared. So this one equals 2, the inverse sine of u over x, or x over a, which is just x. So c, which makes it 2x plus c. So put these two together. This is plus c also. Put these two together, and you get your answer. -3 radical 1 minus x squared plus 2 inverse sine of x plus c. We're simply doing it by parts. Actually, to be honest with you, that's one of the easier ones so far. Okay, maybe not. So much for the easy ones. As I said earlier, it looks simple once you get going. How do you know how to start, what process to use? Trial and error. If one way doesn't work, try another one. But we could look, since we looked at 6 examples so far, we could do a rule of thumb. If it's algebraic, well, see if long division will work. If it's an improper fraction. If it's a proper fraction, well, see if it's du over u. If it's trigonometric, use a trig identity. Again, it's all trial and error from there on out until you start better seeing them better. Example 7. Evaluate this function. One plus radical x. Oops. Damn it. It's 1 plus radical x cubed. Well, what method do we want to start off with here? Let's use substitution. I mean, that's always the safest way to go. So what do we have? And then what would du be? Well, we take a derivative, forget the derivative of 1 is 0. So derivative of square root of x, it's 1/2 x to the power -1. So it's 1 over 2 radical x dx. So does that help us any? No. Hold it. Let's look at this. What is dx equal? If we solve for dx, what do we get? Multiply this. So we have dx is equal to 2 radical x du. Okay. So we have 2 radical x du. What's radical x? If we solve for radical x, we get u minus 1. So radical x is u minus 1. So dx is 2 u minus 1 du. And on the bottom, we have 1 plus radical x is u minus 1 cubed. The ones cancel, so we have u cubed. As we can see about that, we have 2u minus 2 over u cubed. See if we do this again. So with this one, so we have integral so what's the this is squared. So we have is 2 du u squared. I just get myself in a circle. U. Why would this method not work? Remember, I said trial and error, right? Why would this not work? U over u. So I have, I'll put the 2 out in front. Okay, let's put those back in there. 1 over 2 square root of x dx over 1 plus radical x squared. What's that? Good question. I think it was this. Dx is 1 plus radical x cubed. So actually I got myself in this corner down here. Oh, hold it. Let's get back to the same thing. Okay, what's that going to give me? This is just for this first one. Okay, so I can't use that method. I have this correct. Two U. Oh, hold it. I was looking at this all wrong. This could still work. Because if we had two, that's what I did wrong. I forgot that these were on the denominator, so they're negative exponents. So let's leave these like this, because now the rule says add one on top. So we have 2u negative 2 du minus 2u negative 3 du. The integral here would be add 1 over negative 1. That's where I messed up. So this becomes negative 2 over u. The negatives cancel. The 2's cancel. So it's 1 over u squared plus c. Excellent. Get a common denominator. So I have u squared on the bottom. It's negative 2u plus 1 plus c. I can rewrite that. What would u again? So we have here 1 plus radical x, 1 plus radical x squared, one minus 2 radical x over 1 plus radical x squared. -1 minus 2 radical x. Oh, plus c. Yeah. I was thinking it backwards. I was taking derivatives instead of the integrals. Yeah, that one used a couple of our rules. This is as far as I can go. And again, this whole function is continuous on the entire domain because the bottom can never equal 0. All right. And example 8. Evaluate -pi/2 to pi/2 x cubed cosine x dx. We will cover product rules for integration. But I mean, think about it. It's not a cosine u du because it's a higher exponent. Another way we could look at that, I attached it to your sheets, that single sheet, theorem 8, I believe it was. What's happening here is this. If you look at the bounds of integration, we're going from -pi/2 to pi/2. So we have -pi/4, positive pi/4, and 0. 1, -1. What's going to happen with cosine? At 0, what is cosine? 1. At pi/2, cosine is 0. Makes sense? So this is just for this part. So we'll get a positive answer. It's this area plus this area. But how about cube root of 3? What does the cube function look like? Right, it looks like this. Which means that this area here and this area here, if you add them together, what happens? They cancel out. So this area is 0. This area is twice whatever that is. Twice, I call it x. So when we multiply them, 0 times anything is 0. Simply because we're looking at symmetric integration. And that's why I put the pictures on there. If it's the same top and bottom and they cancel each other out, then it's zero. If you look at sine function, if we look at the sine function from pi over 2 to negative pi over 2, at 0, sine is 0. At pi over 2, it's 1. At negative pi over 2, it's 0. So the area of this would be 0. And that's why in calculus 1, you learned if your areas ever become 0, you can change the bounds of integration. Since both of these are equal, I could change this to twice from 0 to pi over 2 if I wanted to. And then I can find this area and double it, and that'll be both of those. But that's for manufacturing. So a function like this is an even function. What is an even function from algebra? If I put in x, I get a y value. If I put in negative x, I get the same y value. An odd function is just the opposite. If I put a positive, I get a positive. If I put a negative, I get a negative. And that's why they wash out. Odd functions on the same bounds, our symmetric bounds, are always 0. So anything times 0 is 0. Because there's not much we can do with this equation otherwise. We have to look at the functions themselves. Are they odd? Are they even? If they were both odd, no problem. It's 0. If they were both even, problem. That comes later on in this course. But if we have odd even or even odd, then it's 0. Simply because we're looking at equal distances from the 0. And that's it. I know it seems easy. But you saw in the question number 7, you have to go through all possibilities you can. If you get stuck, try something else. But if it's algebraic equation, algebra shortcuts will work. If they're trigonometric, algebraic or trigonometric functions will work. And if they're a combination, use algebra then.